Hi, and welcome to this lab course in electrochemistry. Before we start, in this lab it is very important to us that we are all safe, so we are always wearing our lab glasses, our lab coat, and in our case also chemical resistant gloves. To start our experiment, I will show you first the parts of our setup. This first part here will be our working electrode. You can see that we have on top a platinum disc with a controlled diameter of 3 millimeters. Next, we have the counter electrode. This too is platinum. However, the area is not as defined as for the working electrode. For durability, this electrode is encased in glass. We will make use of a 3-electrode setup. This means that we will also use a reference electrode. In our case, we will make use of a silver-silver chloride reference. This means that this wire inside is silver and it is encased in a solution of silver chloride. This whole item is a half cell on its own. It is in contact with the rest of the cell through this frit. Only ions can exchange over this area. Once it is inside of our solution, this half cell will also generate its own potential. Why would we need such a reference electrode? Electrical potential is a relative quantity. If we want to know the potential at a certain point in an electrical circuit, we have to compare it to another point in that circuit. We can't just measure the potential at one point. We measure the potential difference between 2 points in the circuit. In an electrochemical cell, we are interested in the potential at the working electrode. We still have to choose a second point in our system, as we can only measure a potential difference between 2 points. An obvious choice would be to take the counter electrode as a reference point. Let's say we measure a potential difference of 600 millivolts between the working and counter electrode. However, the electrochemical potential of our counter electrode itself depends on the material of the electrode, the properties of the electrolyte, and so on. If this experiment would be repeated by someone else, or even just repeated by yourself but with a different solution or on a different day, the potential at the counter electrode would be different, and the different potential difference would be measured even though the potential at the working electrode would be the same. We need a universal common reference point. That's why we use a reference electrode. This electrode is a stable half cell on its own and it outputs a known steady potential. It's a semi-closed system with only exchange of ions over the ion frit to close a sub-circuit. The universal reference point, 0 volts, was chosen to be the redox potential of this hydrogen reaction. All other electrochemical reactions are referenced to this potential. However, this is not a convenient electrode, as it requires hydrogen bubbling, so for practical reasons we use different stable half-cell reactions to reference our potentials to during an experiment. We use a silver-silver chloride reference electrode. It outputs always a potential of 0.205 volts. This is compared to the output of the hydrogen electrode. As we know this offset potential, we can correct our potentials in the data so it references to the 0 volts from the hydrogen reference electrode. This is a universal practice, so now we can compare the potentials of different reactions under different circumstances to each other, as they are all referenced to the same point. Note that a reference electrode is only used for outputting a potential. Virtually no current flows through the cell. We still need the counter electrode to complete the electrical circuit and make current flow possible. How will we prepare the cell itself? We will put our solution in a simple glass vial. This glass vial will be closed off with this stopper. Of course, it's not completely closed off because you see these large holes. These are for fitting our electrodes. This first hole on the left side is for fitting our reference electrode. This one on the right side will fit our counter electrode. And the one in the middle will fit our working electrode. Of course, you can see that this area is still slightly too large for this working electrode. That's because we still have to fit it onto the rotor later, and the rotor will close off this hole nicely. You can see that there are 3 more small holes left, one over there and 2 more over there. So why would we use those? These are for the gas purging lines. You can see that we have these Teflon lines coming out from the tool. These are for gas purging. First we will use this line, which is unmarked, and we will fit it into one of the two holes until it reaches the bottom of the cell. The second line, which is marked black, will fit in this second hole. It will only go in so far as to when it is stopped by the marker. Why do we use a cell setup like this? Well, when a solution like ours is in contact with air, there will be gases dissolved into the solution. One of those gases is oxygen. We want to prevent that we measure the reduction of oxygen on top of our own experiments. So we want to get rid of all the oxygen in the solution, and for that we use nitrogen purging. The nitrogen bubbles will force the oxygen out of the solution. So that's why we have this third hole. While we are purging gas through our solution, we need somewhere in the cell that our gas can escape. This will occur at this point here. Now, another problem that occurs is when we want to start our experiment, we don't want this gas line to be active because the bubbles will interfere with our solution, and this will have an effect on our measurements. So doing the measurements, we don't want purging. So we will have oxygen coming back into the cell through this hole here. Well, this is prevented here by the second line. This is the headspace purger. This line, which is marked black, will not go into the solution, but it will make sure that at all time nitrogen is being pushed through the headspace so that at all times nitrogen is leaving this hole and no other gases can enter the cell. Finally, we will put this working electrode on the rotor. For this, we will rotate this whole arm up, and you can see that there is a copper connection on top, which is spring-loaded. This is so that we can screw the working electrode nicely on top of this arm, and there will always be a guaranteed good back contact through this Teflon holder. You can see this rubber ring over here. This is a rubber ring that will fit nicely in this big center hole of our cell, like this. Now our cell is ready, but we still have to connect it to this potentiostat. We will use a Parstat 4000. What is a potentiostat? Well, it's actually a very advanced multimeter in combination with a very good controlled current source as well as a very precisely controlled potential source. It can control currents, potentials and frequencies very accurately while measuring the corresponding responses at the same time. To connect the potentiostat to our cell, we will use these cables over here. The first and most important one is this green one, which is immediately connected to a sensing electrode, but together they form the working electrode contact. Because the working electrode is connected to the rotor, we will have to connect this green cable to the back of the rotor itself. Then we have two more cables left. The red one is for our counter electrode, and we will use a crocodile clamp to connect it. And we will have this white connector, which is for our reference cell. This one too we will connect through a crocodile clamp. So aside from our solution, the cell setup is now complete. Okay, so now this is our rotor and the on button is on the back here. And as you can see, we have two distinct parameter areas here on the front panel. The first one is for controlling the rotation and the second one is for controlling the purge. We will start with the purge area. So there is a nitrogen gas line connected to the back of this rotor, and the amount of gas that flows through our cell is controlled by this knob over here. Rotating it counterclockwise will open the line and increase the gas flow. On the other hand, rotating it clockwise will diminish the flow and close the line off completely. As you can see, we have a lever over here with 3 settings. The remote setting is for control by the PC, which we will not use today, and we will also have a set and local position. The set position is the only position we can use in which we can make changes to the purge time. Right now, the time is set to 500 seconds. With this knob, we can increase or decrease this time. For our experiments, we will mostly use 500 seconds. When I put the lever in the local position, the tool opens the gas line, but because our flow is still closed, we counter-rotate this knob over here and open the gas flow. Now we can see that bubbling occurs inside of the cell. If we open the gas line too much, there will be too much bubbles and the bubbles will be too large. These will get caught underneath the working electrode. It will be very difficult to remove these bubbles afterwards. So we try to control our flow just right until we have a fine line of bubbles coming continuously out of the gas line. So now the control flow setting is set perfectly. When I put the lever back into the set position, the purging of the solution will stop. When I put the lever back in the local position, purging will start again, and we will have 500 seconds of purging. After this, purging will stop automatically, and we don't have to change anything over here. Very important to notice is that this second line, which is not into the solution, is constantly purging nitrogen as well. So even now it's purging a little bit of gas. When the bubbling will stop later, the headspace purger will increase its flow and it will prevent oxygen from entering here. So don't worry, in between your experiments, your headspace purger will keep your solution safe from oxygen. Then, for rotation control, we go to the parameter settings over here. Once again, we have the same kind of lever with the same 3 settings: remote, set and local. Once again, only in the set position can we make changes to the rotation speed. Right now it's set to 100 RPMs. This is the lowest setting we will use today. By turning the knob, we can increase or decrease the RPM speed. Once we have chosen our speed, we can put the lever in the local position, and the number that is displayed here will be the actually measured rotation speed. Let me demonstrate. I'll put the lever in the local position, and you can see that the number increases from 0 to 100 when we reach the actual speed. And here in our solution, although difficult to see, you can see a working electrode rotating. For our first experiment, we will examine our background electrolyte. This is so we can determine which kind of reactions are coming from the background electrolyte aside from the reactions that will occur for iron chloride in the solution. We will start by measuring 80 milliliters of our background electrolyte. And we will pour it into our glass cell. Of course, we will close off our flasks and we reassemble the cell setup. Make sure for this first experiment that all electrodes are cleaned first with deionized water. Don't forget to connect the reference and counter electrode. And now, because our electrode is a flat surface, there is a real possibility that when we bring it into our cell, there will be gas bubbles trapped underneath. So what we will do first is to take a little bit of our solution using a pipette and bring some drops on top of our working electrode. This way, the surface is wetted and chances of capturing some air are decreased. There we go. And we close. Before we do anything else, we use this little mirror on the bottom to check if there are bubbles still trapped underneath the surface of our working electrode, which is currently not the case. So now we can attach the gas lines and we're all set.
So, now that the setup is ready with the indifferent electrolyte solution in the cell, let's go into how to execute our first experiment. Right after opening the Versus Studio software, this is what you will see. Now, we would like to create a new experiment in order to measure the IV curves for our indifferent electrolyte solution, first without nitrogen purging and afterwards with purging. To do so, let's go to Experiment, New, Cyclic voltammetry, multiple cycles. Let's click OK. Now we would like to save it as 2.1.A for non-purging. So now if we would like to see what this procedure will do, we can click in Help, and here it gives the schematics. So now we can start setting the input parameters. So let's set this not used to initial potential 0 versus OCP. So we set this initial potential to OCP value. Then we will go to -1 volt versus reference, 1.2 versus reference for the second vertex, and then we will go to not use, scan, 0.02, and 2 cycles. And now we have all our input parameters ready. The only thing left to do is to click Run. So this same process will be performed for all measurements on this section, which is section 2, current potential characteristics. So now that we have obtained our data, let's take a look at it. First, we will compare our indifferent electrolyte solution with and without purging from section 2, current potential characteristics, practical part 1. Therefore, let's take a look at how to import the first file. Let's go first to Experiment, Open, and let's import the file 2.1a. So here you can see only one cycle. This can be actually changed by clicking the tabs segment. Now you see 2 cycles, and now you can see all the cycles. So it's really important. If you're not seeing these segments over here and you are just seeing the data, you just need to click Data Filter. Okay, now we have the data for the indifferent solution without purging. In order to add the purging one for comparison, you can go to here, which is the Overlay Manager. There a new tab will appear over here, and then you could click in Add, Browse, and you can add your second file for comparison. Now you have an overlap of the 2 files. So in this graph, the main features you will have to explain are the following. Why there is an increase in the cathodic current while going below 800 millivolts, why there is a peak at around -400 millivolts, why there is an increase on the anodic current while going above 1.1 volt, and what is the difference observed between the purging and no purging in the region of 200 millivolts. In order to answer these questions, take into consideration what do you have present in solution, which in this case is that we have an acidic solution, therefore there is protons, as well as your solvent, which is water, and a salt, which in this case is KCl and is inert. Taking this into consideration, please determine which reactions are occurring in each of the mentioned areas. Additionally, in order to get the graphs for the report, you can actually just click here and click Copy Data as Image. If you don't want to use the image as it is here, you can also copy the data as text and do the processing of the data with a different software.
So now our experiments with the background electrolyte are finished, and we can deconnect all our connectors from the cell. And we can take out the working electrode from our solution. Be very careful, fix it, and turn the arm up for safekeep. We can remove the gas lines, the reference electrodes, and the counter electrode as well. Our background solution can go into the acid waste. Because our next solution will be the same solution as the background solution, only with iron chloride added, there is no need to rinse the cell, because the water that stays behind will only dilute our solution more. So we can directly add our iron chloride solution to the cell. Again, we measure 80 milliliters. Close our flask and pour our solution into the glass cell. Now we reassemble the cell once more. The Teflon stopper, the reference electrode, the counter electrodes, our gas lines, and finally the working electrode. Don't forget to wet the surface before putting the electrode into the solution. And we press the arm down until we hear the click from the rubber stopper. Once more, don't forget to reattach the counter electrode and the reference electrode. Now we need to look out for which experiments are in need of purging. For the first experiment with iron chloride, we will use a 500-second purge. Therefore, I will put the lever into the local position. Now we are ready for the next experiment.
Now, let's take a look at the data from section 2, Current Potential Characteristics, Practical Part 2. We can import the data as done previously for the first section by going to Experiment, Open the 2.2a, and then going to the Overlay Manager, and then Add, Browse, and add the second one. Okay. Now, in this section, please you have to identify the anodic and cathodic peaks here present, and as well as the reactions happening at each of these peaks. You need to explain the difference observed in the first cycle, which is clearly seen in this section, whether you go first to the positive potentials or first towards the negative. In order to explain this, you should take into consideration what is the oxidation state of the iron species in the start of the solution. Additionally, in order to determine the forward potential, you can use the following feature to do so. So you can basically select the peak with the left click and then just click peak analysis, and then here you will have the values of your peak that you can use to determine the formal potential. So now that we have chosen the potentials at which we want to run our chronoamperometry, let's take a look at how to set our chronoamperometry experiment. In order to do so, let's go to Experiment, New, Chronoamperometry. Let's click OK. Just save it as, and as before, I showed before, if you click Help, this is what the procedure will do. So we'll start OCP and then we'll do a step at a constant potential for a certain amount of time. So we want to set our potential, we set at 400 millivolts, so in this case 0.4 volts versus reference. For 0.05 seconds time per point and a duration of 10 seconds. So now that all the parameters are filled, we are ready to start our experiment. Let's click Run. So in this section 3, we will use chronoamperometry in order to determine the diffusion coefficient of the iron 3+. Chronoamperometry is a technique in which the potential of the working electrode is stepped and the resulting current from Faraday processes occurring at the electrode is monitored as a function of time. Based on the obtained current transients, the diffusion coefficient can be calculated. Therefore, before setting the chronoamperometry experiment, we need to determine at which potentials we will be performing these experiments. As explained in the guideline, for that we will choose two potentials based on the IV curve from section 2, practical part 2. So if we look at that data, in this case, we can clearly see that maybe before the cathodic peak and after the cathodic peak, we could take, for instance, around 550 and 400 millivolts to take the chronoamperometry experiment. So now that we have chosen these potentials, we are ready to set our chronoamperometry experiment. So now that we have obtained our chronoamperometry data, let's take a brief look at the data. This is how it actually will look like. Now, for you to do the data processing, the most important part is to actually able to extract the data, as you cannot use the graph as it is. And to do so, just click here and copy data as text. And then you can actually do all the data processing, maybe in a different software.
So for the third part of the session, we are again going to be doing cyclic voltammetry experiments, which basically means we are going to be applying a voltage on the solution while measuring the current in order to gain better understanding of what the actual behavior of the solution is. Now, the main difference between the first time that we did it and this time is that now we're also going to be looking at the influence of changing the scan rate of the experiment. So basically, we'll be varying the speed at which the voltage changes over time. So for the first experiment, we will open a new cyclic voltammetry experiment with multiple cycles. We will save this experiment as experiment 4.1. And actually the purpose of the first experiment is that we want to obtain a nice standard graph that's centered around the formal potential that we calculated earlier. So again, we will start the experiment from 0 volts versus OCP, which basically means that we start from an equilibrium position where no current is expected to flow yet. And we will use the formal potential that we calculated in one of the earlier questions as the midpoint of our scan. So in our case, the formal potential was calculated to be 500 millivolts. So for the lower limit, we will take 500 minus 200 millivolts. So we end up with 0.3 volts versus reference of the lower point. And for the upper limit, we will add 200 millivolts. So we end up with 0.7 volts for this experiment. Now, for the initial scan rate of this experiment, we will be using 20 millivolts per second, which is the same as what we used in the earlier experiments. So 0.020 volts per second. And with these settings set, we can then run the experiment. Now, in this case, we already have the data, so I'm going to open it quickly. So this is what the data should look like if you did the experiment well. And we can see that we have the nice graph again that's nicely centered around the formal potential, which is nicely in the middle of our scan. So this is what the data looks like, and this is basically a textbook example of a reversible cyclic voltammetry experiment. So after this, we will be repeating this experiment, but this time we will do multiple experiments at different scan rates. So again, we will open a new cyclic voltammetry experiment that we can save as experiment 4.2. We can use the same voltage window that we used in 4.1. So again, a initial voltage of 0 volts versus OCP. a lower voltage of 0.3. Like I said earlier, this depends on the formal potential that you calculated. And then we start with a scan rate of 10 millivolts per second. Now, because we want to do multiple experiments, we can basically just duplicate this experiment that I made here. For the second experiment, we will leave the initial voltage as not used because we wanted to continue the scan. And this experiment, we can copy it and paste it 6 more times. So 1, 2, 3, 4, 5, 6. And now we can start filling in the scan rates that we need to use throughout this experiment. So the first one is at 10 millivolts per second. The second one will be at 100 millivolts per second. The next one will be at 200 millivolts per second. The fourth one is at 20 millivolts per second. So this is the standard one. And we do 50 millivolts per second. After this, we do 500 millivolts per second. All of these numbers are, of course, indicated in the lab course material. Then we have 1 volt per second, so quite a fast scan. And then finally, we end with the first experiment again. So we go back to 10 millivolts per second. Now, in between these experiments, we want to actually rotate the solution for a moment because we kind of want to reset the solution between the experiments. Otherwise, the previous experiment may have an influence on the next experiment. So to do this, we will click Insert. We click Advanced Actions. We add a time delay. And with this, we can define a time delay of 30 seconds that we can have the experiment basically wait between these scans. So we will copy this and duplicate it about 4 more times. And we can start putting them in between the experiments. Now, the point of this is that the diffusion layer that builds up during the experiments may influence the next experiments. So we want, of course, to remove this diffusion layer, and we do this by rotating the experiments. So in these 30 seconds of time delay that we have set here, we will quickly engage the rotation and then quickly disengage it so that the next experiment can begin. And so what we have set up here now is 8 experiments that will go after another. And with each experiment, we will do a scan with the same voltage window, but at different scan rates. And with this, we can now start the experiment and see what results we obtain. So now we can have a look at what the data from this experiment actually looks like. So we can open the data from experiment 4.2, which is this one. And we can instantly already see that the scan rate does indeed have quite a large effect on the behavior of the experiment. We can see that the peaks of the experiment, which were done in otherwise identical conditions, change quite drastically with the change in scan rate. Now, if we close all experiments by pressing this button right here, and we close all the segments, we can compare the first experiment, which is this one, that was done at 10 millivolts per second. We can look at the peak current of this experiment and see that we had a peak current of about 40 microamps. And if we compare this to the second experiment, which was done at 100 millivolts per second, we can see that in the second experiment with the higher scan rate, we have a much higher peak current that's close to 160. So we can see that indeed the scan rate has a quite significant effect on the position of the peak in terms of its voltage and its current. Now, the main reason for this is that the solution cannot quite follow with the fast scans that we are doing. So because of this, the current increases with higher scan rates. Now, this has also something to do with the reversibility of the reaction and also with the diffusion coefficient of the species. And actually, by using the Randall-Ševčík equation, which is given in the course material, we can determine the diffusion coefficient of our active species. Now, in order to do this, we have to determine the peak current and the peak voltage. And to do this, we can click this button right here that says peak analysis. So first we select the peak, then we can click this button, and we can basically read the peak voltage as this value right here. So in this case, it's 536 millivolts. And to determine the peak current, we have to hover over the peak, and we can read the current as the second number in this box. So in this case, it's about 38 microamps. So these numbers, we can use them to determine the diffusion coefficient of the species. And we can also make some plots that show the position of these peaks versus the scan rate. And this will give us some more information on the reversibility of the reaction.
When our working electrode is in the solution and we apply a potential to it, the electrode surface will get charged. In this example, we have an accumulation of negative charges at the electrode surface. These negative charges will attract positive ions from the solution, which will form a positively charged layer at the electrode surface. In turn, this will attract negative ions in the solution. Together, they form a double layer at the electrode surface. The equivalent electrical circuit of the system looks like this. The double layer can be modeled as an impedance, which is equal to a parallel arrangement of a capacitor, CdL, and a resistor, RdL. We can only measure the resistance between the tip of the reference electrode and the surface of the working electrode. If we're only interested in the resistance of the electrolyte solution, we'll have to find a way to bypass the impedance of the double layer. We can do this by using an alternating potential signal. We consider two extreme cases. In the first one, we evaluate what would happen if we use very slow frequencies. Let's say the frequency is so low we can represent it by a direct current. In this case, the capacitor will quickly charge, after which there is only current flow through the two resistors. And we will measure the sum of the double layer resistance and electrolyte resistance. On the other hand, if we use a high frequency signal, the capacitor will induce a time shift of our frequency signal, but will otherwise act as a short, completely bypassing the resistor of the double layer. We now measure only the resistance of the solution. Okay, so now we're ready to set up our experiment. We will apply a frequency to our system, so we are going to choose Experiment, New, and we will do a potentiostatic EIS, which stands for Electrochemical Impedance Spectroscopy. Click on OK, and we give our file the name 5.1, enter. All right, so here we get the baseline values that Versa Studio gives us. They're not close enough for our system, so we'll make some adjustments. First off, our starting frequency will not be 10,000, but 100,000 hertz. This is something we know from experience. We have to go to this high a frequency to make sure we bypass the resistor in our double layer and short our capacitant. An end frequency of 1 hertz. Well, this is fairly okay, but the thing is, this is only interesting if we want to go to very, very slow frequencies, and they are interesting for determining what the resistance of the double layer is. However, this is not asked here, because if we really want to go into a steady value, our frequency has to go so slow that the experiment will take forever. So we will end at a frequency of 10 hertz. So where will we apply this frequency? Well, we will apply it around the open circuit potential. So we have our potential 0 versus OC, and the amplitude of our frequency will be 10 millivolts. Everything in this area here is just the scan properties, which are already fine. Our plot will be logarithmic. The number of points we will collect in the end will be 30. And the points per decade, so how many samples we take, is 10. So this is fine. We can now start our experiment by clicking here on the Run button. We finished our measurement, and we can see that Versa Studio opened 2 tabs, so 2 different representations of the same data. This first representation is called the Nyquist plot, and it plots the real and the imaginary part of our complex resistance as a function of each other. Well, we will not go into much detail of this representation because it's outside of the scope of this lab, but I can tell you that this kind of representation is of interest if you want to model the equivalent electrical circuit for your electrochemical cell. We are going to this first step, and this is called the Bode plot. And it plots the absolute value of the resistance as function of the frequency we applied. As we start here at 100,000 hertz, we can hover over one of these points in the plateau and we can see what the values were that we measured at this point. If we go to the other end of our measurement at 10 Hz, we can do the same, and we can see that we're not completely in a plateau yet, but we can make an estimate of where we were going to by looking at these data points. These are of interest for your report.
So now we can move on towards the final part of this session, in which we will be testing the use of a rotating disc electrode and see how this affects the performance of our system. Now, in previous experiments and stationary conditions, we've already seen that in our cyclic voltammetry experiments, we see the formation of a peak. So we see actually that with increasing voltage and increasing time, we see that the current will decrease over time. We have explained this fact by the formation of a diffusion layer, an area in which the active species will be much lower in concentration. And because these active species is what is actually reacting, and they have to come from the bulk solution and be transported towards the electrode surface, we see that the current will decrease over time because of this. Now, this situation will be completely different if we use a rotating disc electrode, due to the fact that when we are using the RDE, we will actively stir the solution, which means we are pushing the active species from the bulk solution and pushing it towards the electrode surface. So this will completely change the behavior of the system. Now, we will be analyzing this in this experiment. We will first be doing cyclic voltammetry experiments again. So we start an experiment with multiple cycles. We save this experiment as experiment 6.1. And the purpose of this first experiment is that we will again be varying the scan rate. We've already established that the scan rate has an important effect on the experiment when we are doing it in stationary conditions. We can also expect it to have an important contribution when we are rotating the disc electrode. So we will set the limits of our scan. So we will start from OCP, or 0 volts versus OCP, the equilibrium position. And we will scan towards a lower potential of minus 0.1 volts versus the reference. And the first scan we will do is at 5 millivolts per second, which is a really slow scan rate. We will be doing 3 experiments, so we will copy paste this experiment 2 times. The second experiment we will be doing at 10 millivolts per second, and the third experiment we will be doing it at 50 millivolts per second. Now, the reason we are changing the scan rate is that the slower we do the scan, the closer we are towards steady state conditions, which means we will get closer to the true value that we would expect for the current at that position. Now, these very slow scan rates also mean the experiments take very long. This 5 millivolts per second experiment takes quite a long time. So the purpose of this experiment is to see how fast can we do the experiment while maintaining reasonable results. So with the parameter set like this, we can put the rotating disc electrode to 240 RPM and start to run the experiments. So these are the results that we got from this rotating disc electrode experiment, and we can quite clearly see that the results are significantly different from what we are used to. Now, to explain this, I'll open only one experiment for now. We can quite clearly see that we no longer have the formation of a peak, but instead the current seems to level off at a plateau value. The reason for this is that we already explained that the formation of a peak is due to the formation of a diffusion layer that will grow over time. Now, as we are rotating the electrodes, the diffusion layer will actually no longer grow over time because we are actively pushing the active material towards the electrode surface. This will cause the diffusion layer to be a constant thickness, and the replenishment of the active material will no longer change with time. So because of this, we see that the current we measure is also stable over time. So that's why we call these experiments also steady state experiments. We also see that on the return scan, we no longer have the formation of an oxidation peak. This is because the species that we have reduced in this area will be washed away, so they cannot be oxidized in this area. Now, the point of this experiment was that we would compare the effect of the scan rates of the different experiments. And we can quite clearly see that the faster scan rates will lead to a more deviation compared to the slower scan rates. So the point here is we want to see how fast can we scan without this deviation becoming too big of an issue. That's why we want you to also plot the current we see at, for example, this point to the current we see at this point for all different scan rates. So after we have selected our desired scan rate, we can now move on and look at the influence of the actual rotation rate itself. We've already seen that the rotation rate has a significant effect on the experiment, but what happens if we change this rotation rate to different values? So to test this, we will again open a new cyclic voltammetry experiment with multiple cycles, like we did before. We will name this experiment experiment 6.2. And we will again use the same window for our scan. So we start from 0 volts versus OCP. We scan towards a lower voltage of minus 0.1 volts. And we use the scan rate that we selected earlier. For this experiment, we will do it 5 times because we will be doing 5 different rotation rates. So we will duplicate it for 5 times. Of course, in between the experiments, we also have to have the chance of changing the rotation rate. So that's why we also have to add a waiting step to the experiment again. So time delay of about 30 seconds. We duplicate this again for 4 times. And we place it in between the experiments. So this gives us a chance to actually change the rotation rate of the experiment so that each cyclic voltammetry experiment that you see here will be done at a different rotation rate. So this we can use to test the effects that the rotation rate has on the experiment. This experiment shows the influence that the rotation rate has on the actual experiment. We can see that the value of the plateau really depends on the rotation rate. Basically, with increasing the rotation rate, we also increase the current of this plateau value. Now, this actually makes sense because at increased rotation rate, we end up with a diffusion layer that is much thinner. And this is because as we increase the rotation rate, we are much quicker pushing the material towards the electrode surface, and therefore we can measure more current as these active materials are being consumed in the experiment. So for the final experiment, we will be doing a Karakterisatie analysis in which we are basically comparing the effect of changing the rotation rates while using different voltages. We do this because we have to realize that if we look at this graph, we will see 3 different contributions. In this first area, we see that the current is actually increasing exponentially with the voltage. This is because this is a purely kinetic limited area. Now, after this, we see that in this middle area, we see that the graph becomes a bit more linear. This is because we, on the one hand, have the kinetics contribution, but on the other hand, we also have the diffusion limitations. So because of this, the graph starts to lose its exponential increase and becomes a bit more linear. In the final area, we see that the current will actually start to level off. And this is purely because of diffusion limitations. So these are the 3 regimes that we see in this area. So we have the kinetics limited regime, we have the mixed regime, and we have the diffusion limited regime. Now, by doing a Karakterisatie analysis, we can actually gain some more information about these 3 different regimes. So for this experiment, we will be choosing 3 voltages in this area. So 1 in the kinetic limited area, 1 in the diffusion mixed area, and 1 in the diffusion limited area. And we will be keeping the voltage constant at that value while changing the rotation rates. So to do this, I will open a new experiment. Oh, by the way, we will be doing an example at 500 millivolts. So that's this value right in the middle. So we will be opening a new experiment, a chronoamperometry experiment. We save this experiment as experiment 6.3. We also indicate the value of the voltage that we choose. We save the experiment. And now we can actually set the voltage that we will be doing. So we will be doing 500 millivolts, like I said. We will be doing a time per point of 50 seconds. And we will be doing the experiment for 10 seconds. Now, we are going to be doing this for every rotation rate that is indicated in the lab course. So we will duplicate this experiment 5 times. But of course, we also need a waiting step in between. So we add this as the time delay of about 30 seconds. This waiting step is again so that we have a chance to change the rotation rate between the experiments so that we can have a unique rotation rate for every experiment. So we place it again in between the experiments. And so now basically every experiment that we do will be done at a different rotation rate, and we will be looking at the effects of the current as it responds to this. So these are the results from the experiment at different rotation rates, and we can quite clearly see that again the current seems to level off towards a steady value. This value also seems to depend on the rotation rate that we use. with a lower rotation rate giving less current, while a higher rotation rate gives us more current. Now, for the actual analysis, we have to take the steady state current, so one of these values, per each rotation rate, and plot 1 over the steady state current over 1 over the square root of the rotation rate. By plotting it this way for each different voltage, we make a nice Kutteke-Leibniz analysis of each voltage. And in this plot, basically, the slope represents part of the diffusion limited area, while the intercept is related to the kinetics. So by making the plot in this way for the different voltages, we can look at the contribution of each of these effects on the actual current that we are measuring.
Now that we are ready with our experiments, we have to clean up our setup. We disconnect all our connectors, lift the working electrode arm from the solution and turn it up. We unscrew the working electrode and clean it with deionized water. We do the same thing for the counter electrode and also for the reference electrode. And for safekeeping, we put it back in the saturated potassium chloride solution. We remove the gas lines and we can drain our iron chloride solution in the acid waste. That was it for our experiments for today. Thank you for participating in this lab and good luck with making your reports.